So, up to now, we have seen the properties of a probability measure, the definition of a random variable, definition of the distribution of a random variable, and we have seen that to specify the distribution of a random variable, it is enough to specify it on a p-system that generates the sigma algebra, for which the random variable is measurable, I guess. Then we took a look at the definitions of the notion of independence, product spaces, and the general law of total probabilities using transition kernels. Then we started talking about products of kernels, and let's get back to that point. So definition, the product of kernels. So the product of K and F is the transition kernel from the space E to space F, G actually, because we have K, which is from E to F, and L, which is from F to G, such that KL of F is the same thing as K of LF for any F. And the explicit formula is not very clear from the notes, to me at least, but basically the product of kernels is a way to describe how a process can transition from one state to another when we have intermediary steps between them. Something like this, I think. Like, for example, we have, let's say, a stochastic process which goes like this and then like this, and we want to find the probability of getting from here directly to here. So we first use the first transition kernel, which describes this motion here, this, and then this one, something like this, I think. Okay. Now, types of kernels. So we say that a transition kernel from E to it into itself, so it takes values in the same space, is called Markov. If K of X and E is 1 for any X, I think. Yes. So if we consider what is the meaning of this, the kernel on the entire space. So when we use the kernel as a measure on the entire space, this should be 1, which means it's a probability measure, I think, sub Markov. If, I guess, basically the same thing but less than 1, yes. And what do we have? And we have, since kernels are also measures, we can categorize it with all the types of measures that one sees in measure theory. So sigma finite, capital sigma finite, sigma bounded, capital sigma bounded. And now we define the powers of a transition kernel, which is a generalization of the product of kernels, I think. But here we have that the kernel is still in the same space. So given a transition kernel on E, its powers are defined recursively as follows. K of k to the 0 is the identity, k to the 1 is k, k to the second power, k squared is k times k, I think. And so on, and k to the n is k to the n minus 1 times k. And here the identity is nothing but the Dirac measure of the set A. No, here it writes it like this. The Dirac measure of x sitting on A, which corresponds to this thing here. So here we have the link between the Dirac, the delta Dirac, and the indicator function. So here, if x falls in the set A, we get 1. If x falls into the set A, we have 1. Or actually, if A contains x. Question. How to interpret this? So in this way, we use kernels to construct the transitions of a stochastic process, basically, I think. And this should be related to finite dimensional distributions, which I still don't understand very well. So, classification of kernels, as I said before. Okay, so a transition kernel from space C to space F is said to be bounded if, considering it on the entire space, we have that it is finite. But this should be the second space. Finite. I don't know why I wrote. Bounded if this thing here so this function, because when we associate to x stuff, the kernel is a function, so this thing here is bounded, is a bounded function. Then sigma finite if the measure is sigma finite and do I remember what is the notion of sigma finite? Of course not. Damn. Sigma bounded, there exists a measurable partition Fm of f such that the function here is bounded, right? Bounded for any n. And it should be for any x also, I think. Then we have that it is capital sigma finite. And this will be important for the following theorem. If this thing happens, the infinite sum of Kn for some sequence Kn what is Kn? What does this mean? And another question can be examples of all these things. Finally, we have that this capital sigma bounded if, I guess, this sum is bounded. Oh no, if the Kn can be chosen bounded. But what is Kn? And finally, if kxf is 1 for any x in f, for any x in e, okay, then it is called the probability kernel. So it is basically, what is the difference between Markov kernel and probability kernel? I think that a Markov kernel is a probability kernel, but not vice versa. Maybe. I don't know. With this said, let's go with the following proposition. Okay, let K be capital sigma finite. From E to F. Then for any F, in the product sigma algebra, which is positive, we have the following thing. Df of x is the integral over f k of x dy f of x and y for any x in E. This thing defines a function df which is measured with respect to E and positive. So let me write it again for practice. Let K sigma finite transition kernel from E to F. Let's just write from the space E to F. Then for any function which is measurable with respect to the product algebra, well, this is the same. We have that df of x is the integral over f, k of x dy, f of x and y. For any x in E, a function df in E. Moreover, the transformation df, no, just t from the products in algebra to E plus is linear, right? Is linear and continuous under increasing limits. Continuous under increasing limits, which means that t of af plus bg is the linear combination at of f plus bt of g. The parenthesis is useless actually. For any a and b real numbers. And second, the continuity. So t of n increases to t of f for any positive sequence of measurable functions in this thing here, no, in the products in algebra. So what is the meaning and use of this result? So we have a transition kernel which is capital sigma finite, which means that the infinite sum of the kn, which I don't remember what I don't know what they are. Anyway, if we have that k capital sigma finite, then this function is linear and continuous. And this is the analogy with kf in the theorem of the general law of total probabilities. Point 1, the first point. So this If we have this, we have that it is linear and continuous. This is the important thing. Now we get to another important theorem. Extension of measures on product spaces. Which says the following. Let mu be a measure on the space E. K, capital sigma finite, transition kernel from E to F. Then by F, so the product measure between these two is the integral over E mu dx, integral over F, K of x dy, F of x and y, right? Yes. For any F in the product sigma algebra, which is positive. Moreover, if we know that mu is sigma finite, so this thing defines a measure pi on the product space. So if we have a transition kernel measure, we get a product measure. A measure on the product space. If mu is sigma finite and k is sigma bounded, then pi is sigma finite, and it is the unique measure such that the measure of a measurable rectangle A cross B is integral over A mu dx K of x and B for any A in E, B in F. Let's try to do it again. So how can I call this? Extension of measures on product spaces. EMP. Extension of measures on product spaces. Let mu on E. K which is capital sigma finite on from E to F. Then correct. Then we have that pi f is the integral over E mu dx, integral over f, fx dy, f of x and y, for any f. This defines a measure pi on the product space. Moreover, if mu is sigma finite and k sigma bounded, pi is sigma finite, and it is the unique measure such that pi of a cross b, so the measure of this rectangle, this Cartesian product, is the integral over a mu dx, k of x and b. For any a in the sigma algebra E and for any b in the sigma algebra F. Oh, okay, good. It takes quite a good deal of time to remember the results. Here we have a remark. When kxb is actually nu b, the measure of b in this way, so it just depends on E for some capital sigma finite. Measure nu on F. Then we obtain the product measure. So pi is mu F, and the product between mu and nu. Which is the general form that we have when we have independent random variables or independent distributions in this case, because we will see that these measures, well, we already saw that mu is a distribution. Let's make another example of kernel. So we have mu1 on E1, mu2, no, k2 from E1 to E2, and k3 from E2 to E3. No, this is actually from the Cartesian product. This is 1, this is 2. Why? Well, because it is that with this we have that mu1 k2 creates a product measure by, I think, something like that, because of all the theorems that we saw before. So with this, we want to construct a transition kernel. No, a product measure using all these kernels. So you can consider this, for example, if you have a stochastic process, this is the initial distribution for the initial value of the process, and then how it evolves to time 2, and then how it evolves to time 3. So to model the probability, and we want to discover how the joint distribution of getting from this directly to this. Then by f, so the product measure is given by the integral over e1 mu dx, integral over e2 k2 of x dy, integral over e3 k of x1 x2 this is x1, this is dx2, k of x1 x2 and x3, no, dx3 f of x1 x2 x3. With f, which is measurable with respect to the product space, and positive, and I well, and pi can be seen as dx1 dx. If we write it in differential form, is mu dx1 k of k2 of x1 dx2 k3 of x1 x2 dx3. And if we just get rid of the parentheses, it is the composition or the product kernel mu1 k2 k3. So this is how we use transition kernels to construct measures on product spaces. Okay. With this said, we can stop with the transition kernels and talk about expectations of random variables. So definition: let x be a random variable on omega hp, this probability space. The expected value of x is defined to be the integral over omega x of omega dp omega, which is also written more simply like this, or alternatively p of x. So this is the integral of x with respect to the probability measure p. So this is the definition of the expectation, which is basically we integrate over all the values of x weighted by the probability p. So it's the weighted average of the values of x. Example is a natural, is still the expectation, but written more formally in the language of measure theory in some way, with a measure theoretic basis. Like an example, for example, coin. Let's make dice. 1, 2, 3, and 6. The weighted average, considering a uniform probability for all of these, should be 3.5. And it's basically the sum of all the values of x times the probabilities that x is equal to 1, 2, 3, and so on. I, where I is the number of things here. Now here it talks about the change of variable formula for the Peck integral. Change of variable formula. So if we have f in h from the space f to the space c, so here we have actually a reverse thing. Then there exists a measure nu on f such that this corresponds to the integral over e of what? Of mu dx. F of, mu dy, f of y. And here there are some other details, but I think I will review this next time, and I will stop here for the moment and take a little break. Ciao, ciao.